In this lesson, we're going to chat about the polar coordinates and the graph. On a polar graph, such as this one below, the origin is called the pole. So where we would start graphing is called the pole, and the positive half of the x-axis is called the polar axis. A point in the polar coordinate system has the coordinates r, theta. We're going to graph each of the following points by following the directions on how to plot points on a polar graph. First, we need to locate the directed angle from the polar axis to the ray OP. So any of these are going to be the ray OP. Move a directed distance r from the pole. If r is greater, then we're going to move along the ray. If r is less than 0, we're going to move in the opposite direction. So ideally, when we start graphing, we want to start with theta. Typically, when we graph, we start with the first coordinate and then move to the second coordinate. But when we're graphing with polar coordinates, we want to start with theta. So let's say I want to graph point A, which is 360 degrees. So 3 is our R value, and 60 degrees is our theta value. We will start at 60 degrees. So we're going to find 60 degrees here, and then we're going to find the radius of 3, which appears to be here. So this will be A. Letter B, 0, 10. So if I'm at 10 degrees, we're going to be probably about here-ish. However, we're at 0. So about here and 0. That means we're right at the pole. So B is at the pole. Part C, -5, 120 degrees. So I'm going to go first, we know, to 120 degrees. And we're not only at 5, which is this ring, but we're at -5. So I need to go to the opposite side of the pole, which would bring me to here. We could also say that letter C is also the same as 5, 300 degrees. 1, -60. So I'm going to start here, and -60 means we go backwards. So I'm going to go backwards -60. That would bring me at 300, and then I need to go to 1, which is that first ring. So here's letter D. Letter E, 2, 3 pi over 4. We know that 3 pi over 4, according to our unit circle, is 135 degrees. So if I go to the 135 degree mark, which would be here, and then to the ring of 2. Letter F, -4 pi over 4. We know pi over 4 is also the same as 45 degrees. So I'm going to go to 45 degrees. Go to the 4, but then we want the opposite. So I'm going to go to the 4 ring opposite. So here's letter F. Letter G is -5, pi over 4. So I'm first going to go -45 degrees, which we know, again, is going to the right. So -45 degrees would put us here. But I want not only 5, but -5. So that would bring me across to the same as 135, as the same as 5, 135 degrees. So this would be the same then as 5, 135 degrees, or 3 pi over 4. And letter H, we have 3 pi over 4. But hey, didn't we just find that? Since 135 degrees is also the same, G and H are the same polar coordinate point. We are able to convert from rectangular coordinates to polar coordinates and from polar coordinates to rectangular coordinates. We need to recall a few of the relationships that we have built over the semester. Let's first start with our reference triangle. So if this is the point XY, we also can call this the point radius theta, just as we did the previous page. And if this is theta here, we know that we went X value to the right and Y value up top, knowing that using our Pythagorean theorem, we can find the radius as the square root of x squared plus y squared, according to the Pythagorean theorem. We can also square both sides such that r squared is equal to x squared plus y squared. We defined cosine of theta as our x over our r value, since we have adjacent over hypotenuse. Solving for our x by multiplying both sides by the radius. X is also radius times cosine of theta. And similarly, sine of theta is opposite over hypotenuse. Solving for y, we have y is equal to radius times sine of theta. And tangent is opposite over adjacent, or y over x. Let's convert each of the following to polar coordinates. So I'm just going to quickly draw a sketch here of our point 3, 3. So we know it's going to be here. So if this is the point 3, 3, we would go to the right 3 and up 3, and we can find our radius by using the Pythagorean theorem. So the square root of 3 squared plus 3 squared, which is 18. We know 18 is the same as 9 times 2, because I can take the square root of 9. We'll end up with 3 square roots of 2 for our radius. Okay. Now we can find sine and cosine. Sine of theta we know is opposite over hypotenuse, so 3 over 3 square roots of 2. Rationalizing the denominator and simplifying, we end up with square root 2 over 2. Cosine will give us the same value. So 3 over 3 square root 2, rationalizing that denominator, we have square root 2 over 2. Tangent is opposite over adjacent, 3 over 3, which is 1. We also know that 3, 3 is in quadrant 1. So theta must be 45 degrees or pi over 4, based on our location here. So thus, r theta, we know what r is, 3 square root 2, and we know our theta, which is 45 degrees, based on the type of triangle that we have. Or we could have 3 square root 2 pi over 4 if we were to leave it in radians. Note that there are many other possibilities for our polar coordinates, because we know that there's many different locations that have that exact same point value. We could think about using 3 square root 2 negative 315 degrees. We could even look at negative 3 square root 2 5 pi over 4, which would reflect across for us. So there are many different possibilities with polar coordinate systems. Part B, we have the 2 times the square root of 3 minus 2. So thinking about what that triangle might look like, we would go to the right and then down, so we're in the 4th quadrant. So we would go to the right 2 square root 3 and then we would go down 2 units. We need to identify our r value, so we take the sum of our other two sides squared, take the square root of that. So 2 square root 3 times 2 square root 3, if you need a little extra assistance here, we know that when we square it, it's multiplying it twice. That would give us 4 times the square root of 9, which is 4 times 3, or 12. And negative 2 squared we know is positive 4, and the square root of 16 is 4. So now we know our radius is 4. Okay. When I look at tangent, we could find sine and cosine, but tangent is really all we need in order to find the theta value. So tangent is our y value over our x value. So negative 2 over 2 square root 3. When we simplify, we end up with negative 1 over square roots of 3. We also know that based on our drawing that we're in the 4th quadrant. So when I look for this value of tangent or sine cosine on our unit circle, I see that theta is 330 degrees, or 11 pi over 6. Thus, when we look at our polar coordinates of our theta, we found our radius to be 4 and our theta to be 330 degrees, or if we want to use radians, we'll have 4 with our radians 11 pi over 6. We also know that there could be many more answers than this. We could also have 4 negative 11 or negative pi over 6, excuse me, for going backwards, or negative 4 150 degrees, which we know is a reflection. Now let's convert each of the following to our rectangular coordinates. So we need to find x and y, which is why we solved for x and y on the previous page with our relationships. So first we're given 10 pi over 3. So we know our radius and we know what theta is here. So we know x is equal to radius times cosine of theta, replacing r with 10, which is our radius, and our theta with 10 over 3, pi over 3. We know when looking at our unit circle that pi over 3 of cosine is 1/2. So 10 times 1/2 gives us 5. To find our y value, we use our relationship with sine. So radius times sine of theta, or 10 times sine of pi over 3, or 10 times, when I look at my unit circle, sine of pi over 3 is the square root of 3 over 2. And simplifying gives me 5 square root 3. Thus, we know our rectangular value of xy is equal to 5 square root 3. When I look at part B, we have negative 5, 135 degrees. We need to identify, we know that negative 5 is our r value and theta is 135 degrees. I know my x is equal to r times cosine of theta. Our r value is negative 5, cosine of 135 degrees. When I look at my unit circle, cosine of 135 degrees is negative square root 2 over 2, simplifying to positive 5 square root 2 over 2. Similarly, to find y, we use our relationship as r times sine of theta, which is equal to negative 5 sine of 135 degrees. Sine of 135 degrees is square root 2 over 2, giving us negative 5 square root 2 over 2. Thus, our xy values give us 5 square root 2 over 2, negative 5 square root 2 over 2. And we'll want to leave these in their exact values. Let's convert each of the following to polar equation. Just as a heads up, x squared plus y squared is 25. Knowing what we know about equations, this is going to be a circle. And that 2x minus y is 5 we know is linear. We also know that x is equal to r cosine of theta and y is equal to r sine of theta from the front page. Therefore, what we can do is replace x and replace y with the polar equivalents. This then would give us r cosine of theta squared plus r sine of theta squared equal to 25. Simplifying, we can square every part, so we'll have r squared cosine squared of theta plus r squared sine of theta is 25. I'm going to factor because if I look on the right hand and the left hand side, I notice they both have an r squared. So I'm going to factor out r squared of cosine squared of theta plus sine squared of theta. Don't forget our trig identities. We have cosine squared of theta plus sine squared of theta. According to the Pythagorean identity, that is equal to 1. Replacing that with 1 gives us r squared equal to 25. Taking the square root of both sides, I have our radius is equal to 5. Knowing what we know about a circle, if our radius is 5, it would just go in a circle starting at the origin. However, we are now written in polar form. Let's write 2x minus y equals 5 into polar coordinates. Again, I'm going to replace my x and my y value with the polar versions from here. So I will have 2 times r cosine theta minus r sine of theta equal to 5. I'm going to take, and I see that they both have an r in common, so I'm going to factor out r from both sides. And then there's nothing else that we can do. There isn't a trig identity or anything crazy like that. But we should note that this clearly looks more complicated than our linear equation that we're more familiar with. So just note that sometimes polar coordinates are simpler equations so as the r is equal to 5 instead of x squared plus y squared is 25, but sometimes not. Just as we found with 2x minus y is 5, it looks a little more complicated when I have r times 2 cosine theta minus sine theta equal to 5. Just like we're able to convert equations from rectangular equations to polar equations, we can go backward as well. So let's convert each of the following to a rectangular equation. We have r is equal to 4, which I'm very suspicious that might be a circle. R cosine of theta equals 6, and r is equal to 2 cosine theta plus 3 sine of theta. We know that r is the same as the square root of x squared plus y squared from that front page. So this would be equal to 4 then. We can square both sides, giving us x squared plus y squared is 16. And then we're done. R cosine of theta is 6. Note that from our front page that x is the same as r cosine of theta since they're equal to each other. So I will replace r cosine of theta here with x, and we're equal to 6. So here we found a circle. Here we found a vertical linear line. Letter C, though, we have r is equal to 2 cosine theta plus sine of theta. I need to have r's with my sines and cosines in order to replace them with either x or y. So I'm going to multiply everything by r, giving me r squared when I distribute is equal to 2r cosine plus 3r sine of theta. I'm going to now replace r squared. We know r squared from the front page is equivalent to x squared plus y squared. I know that r cosine of theta, anytime I see that, is equivalent to x. And anytime I see r sine of theta, I end up with y. So I now found my graph. Oops. We need to fix that. That's not correct. This should be A3 here. So 2x plus 3y. Now we can say this is complete. Let's make a table of values, plot these points, and draw the curve of r is equal to 1 minus sine of theta. This will end up being a heart-shaped graph called a cardioid. All I need to do is replace all of my thetas with the value of theta given and solve for r. So currently, if I have theta r of 0, 1, and I wanted to plot this point, I would go to 0 degrees first and my r value of 1. Now I need to find 1 minus sine of 30 degrees. Well, sine of 30 degrees is half, so 1 minus half is half, using our unit circle to help us. Okay, so if I go to 30 degrees and go to half, I'd be about here. Okay, 90 degrees, we are given that we'll have 1 minus sine of 90 degrees, and sine of 90 degrees is 1, so 1 minus 1 is 0. So that would put me at 90 degrees at the middle there. And I can continue this same pattern. I'll end up with 150 degrees half, 180 degrees, I end up with 1. 210 degrees, I end up with 1.5. 270 degrees, I end up with the radius of 2. 330 degrees, I end up with 1.5 again. 360 degrees, I end up back at 1, and then we're going to start repeating. So my graph is going to kind of look like a heart. Let's graph each of the following polar coordinates and try to visualize the shape of the curve before graphing it. For any value or any theta, for r is 3, so it doesn't matter what theta is because r will always be 3. And we found that when I have our r as a value, we end up with just a circle with a radius of 3. So the graph will be all points 3 from the origin. So this we know is also the graph of a circle with radius 3 centered at the origin. So it doesn't matter what values I pick, we're going to have a circle around the origin of 3. Let's graph r is equal to 5 sine of theta. Let's see if we can't get an idea of what the graph might look like by putting it into a rectangular coordinate equation. To do that, because sine doesn't have an r value, I need to multiply both sides by r so that I can replace my sine with an x or a y. That'll give me r squared is equal to 5r sine of theta. I know that r squared is the same as x squared plus y squared, and I know that r sine of theta is equal to y. Solving and getting all of my x's and y's together, I have x squared plus y squared minus 5y is 0. I'm not quite sure what graph that might look like, so instead maybe the polar coordinate system would be a better pair for us. We'll make a table of values with theta and our r values. We'll start at 0 degrees. 5 times sine of 0 degrees ends up giving me 0 degrees since we're at 0. So we're going to start our graph at 0 degrees 0 here. What happens if I do 30 degrees? What might our graph do? Well, this will give me 5 sine of 30 degrees, and 30 degrees is half. So 5 times half gives me 5 halves, or 2.5. So I'll go to 30 degrees and 2.5. So here's 1, 2.5. I'll do 90 degrees. This gives me 5 times sine of 90 degrees. 90 degrees on our unit circle is equivalent to 1. So 5 times 1 is 5. So at 90 degrees, we'll be at the ring of 5. Let's try 150 degrees. This will give us 5 times sine of 150 degrees. Sine of 150 degrees is half, so 5 times half again gives me 5 halves, or 2.5. So 2.5. And 180 degrees, using our unit circle chart, 5 times sine of 180 degrees gives me 0, or 0 degrees, so I'm back where I started. So it looks like it's going to be something like this. Part C, we have r is equal to 2 times cosecant of theta, right? So what we need to do first is get rid of that cosecant. So I know that cosecant is the same as 1 over sine, giving me r is equal to 2 over sine. Let's get sine together with r, if you will. So I'll multiply each side by sine of theta, get it out of our denominator. So these two cancel. I now have r sine of theta equals 2. I know that r sine of theta is 2. And r sine of theta is the same as y, so y is equal to 2. This is a horizontal line 2 units above the origin. And I'm sorry, this should have went up above. Since it's 2 units above the origin, we will look at our ring of 2 here, and it's going to be a horizontal line the whole time. So in this case, it was much more nice to turn it into a linear equation to see what it might look like. Our final example here is to graph r plus 1 equals 2 cosine of 2 theta using Desmos. First, we have to solve for r, so make sure when you're using Desmos to follow up or to check your graphs, solve for r first. To solve for r, we would need to subtract 1 from both sides. So this is the graph that we're going to use using Desmos. So transferring over to Desmos, I'm going to put in my my line 1. I'm going to enter in 2 and then my cosine of 2 theta. I'm going to close my parenthesis. Oops. And then subtract 1. It's giving me an error because we're not in polar coordinates. So I need to change my settings. I'm going to change my settings and I'm just going to tap the polar grid option. I'm going to leave my x-axis as listed there. I'm going to leave it as radians, and it's still not liking something. Oh, try adding r. So here it told me that I needed to make sure my graph was set equal to r. So r is equal to 2 cosine of 2 theta. And notice it's giving me the theta between 0 and 2 pi. We only want to see what's happening in between 0 and 2 pi because 2 pi is 1 full circle around. So our graph looks pretty interesting. We can zoom in to see it looks almost like a bow tipped up on its side. So definitely use Desmos in this lesson to help you graph your different portions to make sure that your graph matches what you found algebraically.